In this video, we solve problem 2.3.16 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to obtain a general solution, or obtain the general solution to this differential equation. I want you to notice that we've got a function of x times dy dx here, plus a function of x times y equals a function of x. That makes this a first order linear ordinary differential equation, which is a good candidate for solving with an integrating factor. Now, if the differential equation is separable, it would be better to separate those variables, because we know solving separable differential equations is relatively easy, but it's not separable. If I moved all of the terms to this side, so let's say I add the x squared y to both sides and then I divide by this, I would never be able to factor that result as a function of x times a function of y, because I'd have a y term in the numerator, that x squared y term, that when I did not have a y term over here, I wouldn't be able to factor the y out from both of them. So yeah, this is not separable. So the best approach then is to use an integrating factor to solve it. We start that process by writing the differential equation in what I've been calling standard form, or you can call it general form. I've seen some people call it general form. It's just the differential equation in this form. You've got a coefficient of 1 on your derivative, plus a function of your independent variable times your dependent variable, and that's equal to a function of your independent variable. If the differential equation is in this form, we're going to call that standard form. Some people give that a different name. Okay, so I want this coefficient to be a 1, not a 1 minus x squared. So I'm going to divide everything by 1 minus x squared. And then we'll simplify, and the dE will be in that form. And I call the new dE star, so that's dy dx minus x squared over 1 minus x squared times y equals this expression over here. So you've got 1 plus x times the square root of 1 minus x squared over 1 minus x squared. Now, that right-hand side can be simplified a little bit because a square root is a 1/2 power. And if I have something to the 1/2 power over the exact same expression to the first, I can simplify those. So we could simplify this. And actually, let's do that. Remembering that the square root of a is a to the 1/2 power. So in general, the nth root of x to the m is x to the m over n. This goes in the numerator, the index of the root goes in the denominator. Okay, so we've got that here. And then here I've got a to some power over a to a different power. We remember that we subtract those exponents. So we're going to have a 1/2 power, or 1/2 minus 1. It's going to be a negative 1/2. And then remember, if your exponent happens to be negative, that's the same as 1 over the same expression, but with a positive exponent. So on the right-hand side, we're going to have a 1 plus x, and that's the implied 2 there. It's not the x plus 1 or 1 plus x squared. That's to the 1/2 over that. So we're going to end up with 1 minus x squared to the 1/2 minus 1, that's negative 1/2, which puts it in the denominator with a positive power, just using all of those rules at once. And this is the same thing. Oops, there's a y there. Okay, since it's a first order differential equation, after we write the differential equation in standard form, we identify p of x. Now, p of x is the function multiplying y. Be really careful here. P of x is not x squared over 1 minus x squared. It's negative x squared over 1 minus x squared. There's a plus here. That negative is going to make a difference in the form of the antiderivative of p of x, which means it'll make a difference in the form of your integrating factor. So that negative is very important. You're not just going to be able to multiply everything by -1 later. So we identify p. and we compute the antiderivative of p. And there are lots of ways that you can do this. I'm just going to show you what I think is the easiest way. You could also use long division. Notice that we've got a polynomial over a polynomial. That's a rational function. So the degree and the degree of this polynomial and the degree of this polynomial are the same. Since both polynomials have the same degree, we've got two options. We can either do the long division so that we have some function plus a polynomial over this polynomial where the degree is less than 2, or we can add a well-chosen 0, which is going to give us the same result that we would have obtained using long division. So I'm going to use the well-chosen 0 method. Now with this, the idea is you just ask yourself, well, what do you want this to be? What would make everything really nice and easy? Well, this would be easy if there was a 1 minus x squared there. So I'm just going to add a 1, because then if I had 1 minus x squared over 1 minus x squared, that would be 1, and then we would be fine. So I've just added a 1 to that numerator. But you can't just add a 1 without changing the value of the fraction, so we have to do something to compensate for adding that 1. In addition to adding that 1, I want to subtract a 1. So I'm adding a -1 and a 1 to the numerator. That's just adding a 0. But now, because I've added that 0, I can separate the numerator into two numerators. And we'll have this. We'll have -1 over 1 minus x squared here, plus 1 minus x squared over 1 minus x squared. In calculus 2, we called that separating the numerator. And that's nice because that's a 1. And this I can multiply by -1 over -1. And then I end up here. -1 times -1 is +1. -1 times that quantity, if we distribute it, we get x squared minus 1 there. Then we ask ourselves, do I have a rule for that? And we don't, but that's a difference of squares. Remember, a squared minus b squared, that factors to a plus b times a minus b. So that x squared minus 1 squared can be rewritten as x plus 1 times x minus 1. And we're antidifferentiating that with respect to x. So this is a rational function where the degree of the numerator is less than the degree of the denominator. We've got two linear factors, neither one of them are repeated. So this is an excellent candidate for partial fraction decomposition. So we're going to use partial fraction decomposition for this piece right here. So that requires, starting here, we're going to state the appropriate partial fraction decomposition for that expression. Since I have two linear factors, neither one of them are repeated, my partial fraction decomposition has two terms. Linear factors have constants in the numerator, and we'll have each of the linear factors in the denominator. This is going to be true for some unknown constants a and b. Now we're going to find the constants a and b that cause these two to be equal to each other. In order to find a and b, we're going to multiply this equation by the least common denominator, which is always the original denominator, and simplify. So we'll multiply by x plus 1 times x minus 1. And those will reduce. X plus 1 over itself is 1. X minus 1 over itself is 1. So we have this new equation, which is just this original numerator equals a times x minus 1 plus b times x plus 1. Now, since we have two linear factors, neither one of them are repeated. The easiest way to solve for a and b is to choose the values of x that cause each of these factors to be 0. Then once we do that, we're going to substitute those into the equation. And then we're going to solve for a and b. And the beauty of that is that when you choose a value of x that causes a factor to be 0, then that term disappears in the equation. And then you end up with a very simple equation involving the other variable. So this factor is 0 when x equals 1. So if I substitute x equals 1 into both sides of this equation, I have 1 equals a times 1 minus 1 plus b times 1 plus 1. See, because x equals 1 caused this to be 0, I've got a times 0, which is 0. So that whole thing is gone. And when we what we end up with is 1 equals 2b. So if I want to get b by itself, I divide both sides by 2, and I get b equals 1/2. Now over here, I look at the second factor, and I ask myself, okay, well, what x value would cause that factor to be 0? Turns out -1 would work just fine. If x is equal to -1, we have a 1 on this side, and then we have a times -1 minus 1 plus b times -1 plus 1, and that's 0. And so we get 1 equals -2 times a plus b times 0, which is, of course, 0. So we have 1 equals -2a, so a is just -1/2. We multiply both sides by we divide both sides by -2 to get a. So now we know that this expression is the same as this, with a equals -1/2 and b equals +1/2. So p of x, or the integral of p of x, can be rewritten this way. I've got a -1/2 over a, which is x plus 1, plus b over x minus 1, that's +1/2 over x minus 1, plus 1, and we're antidifferentiating with respect to x. Now, if we had used long division to get from here, or if we had used long division here, we would have obtained this result, and then we would have still had to use partial fraction decomposition for this. So the only thing that's a little different with adding the well-chosen 0 is just how we get from here to here. But once we've done that, we still have to use PFD either way. Okay, so now we want to compute the antiderivative p of x, keeping in mind that e to the integral of p of x power is our integrating factor. So we can evaluate this now. Now on this one, if you factor out the -1/2, you have this. On this one, if you factor out the +1/2, you have that. And then of course the antiderivative of 1 with respect to x is just x. Now for each of these, we can do a pretty simple u substitution. Excuse me. If u is equal to that denominator, du is just a 1 dx. So this is a 1 over u du. Similarly, if u is equal to this denominator, x minus 1, du is just 1 dx. So this is also a 1 over u du, it's just a different u. So the antiderivative of this is the antiderivative of 1 over u, which is natural log of the absolute value of u. The same is true here. We just have u equals x plus 1 on this one and u equals x minus 1 on the second one. And so we're ready to antidifferentiate now. the antiderivative p is -1/2 times natural log of the absolute value of u plus +1/2 times natural log of the absolute value of the other u plus x plus c. Then for the reasons that we discussed in the video over first order linear differential equations, we're going to choose that c to be 0. We don't need infinitely many integrating factors. We just want the one integrating factor. For the first u substitution, u was x plus 1. The second one, u was x minus 1. So when we back substitute, we'll have a x plus 1 here and an x minus 1 here. Now, remember, we're getting ready to take e and raise it to this power. So it's helpful to rewrite this in such a way that that's going to simplify nicely. So what I would recommend that you do is take these two logarithms and factor out the 1/2. I'd write the positive one first. That's natural log of x, absolute value of x minus 1. And then over here, we're going to have natural log of the absolute value of x plus 1 plus x, and we've chosen c to be 0. And then you can see now that without that 1/2 there, this is natural log of a minus natural log of b. We know from pre-calculus that natural log of a minus natural log of b is natural log of a over b. So we can rewrite that as the log of a quotient. Log of a, which is x minus 1, over b, which is x plus 1, plus x. And then we're going to take this and we're going to raise it to the 1/2 power. And the reason we can do that is because we've got a constant in front of a logarithm. And we know that from pre-calculus that that's the same as natural log of that expression inside raised to that constant power. So we have this as our antiderivative of p of x. And now we can use it to define our integrating factor. The integrating factor is always e to that power. Now notice we've got a sum of two terms here. We can rewrite this differently as well. Remember from algebra, if we have x to the n times x to the m, we have that's x to the n plus m. If the bases are the same, we just add the exponents. That works in reverse as well, and it works when the exponents have the variables in it and the bases are numbers. So I've got this number raised to this power, or this plus this power. So it's just like going from this side to this side. We can break this up into two pieces. We can rewrite this as a product of e to this power times e to the x power. And then because exponents and logs with the same base are inverse functions, e to the natural log of a is just a. Those undo each other. And we end up here. Okay, a couple of things that we need to discuss. We can't take the natural log of 0. So obviously, this expression would be 0 when x is equal to 1. That's when the numerator is 0. So x cannot be equal to 1. Is there any other restriction? Well, this absolute value has to be strictly positive, and it is already strictly positive because it's an absolute value. So I think we're fine there. But in order to do the differentiation and antidifferentiation that we'd like to do, it would be nice if we could just write that as this expression raised to the 1/2 power. So we can do that provided that that expression is positive. That assumption might not actually be correct. That assumption, like the sign of this, really depends on which interval we're on. And those intervals are defined by the x values that cause the numerator and denominator to be 0. So let's say we're just looking at this quotient, x minus 1 over x plus 1. Well, x plus 1 is 0 when x equals 1. X plus 1 is 0 when x equals -1, sorry. X minus 1 is 0 when x equals +1. So this factor x minus 1 is going to be positive when x is greater than 1, like x is 2, and then it's going to be negative the rest of the time. And this factor x plus 1 is going to be positive over here, and it's positive over here, but it's going to be negative when x is less than -1. So this is going to be a negative divided by a negative, which would be positive on this interval. It would be a negative divided by a positive, which would be negative on this interval, and then a positive divided by a positive, which would make it positive on that interval. So this absolute value of x minus 1 over x plus 1 raised to the 1/2 is going to be equal to just the square root of that. Whenever this expression is positive, which is on the interval from -infinity to -1, and also on the interval from 1 to infinity. And actually at -1, we're going to have a problem as well because there's an asymptote there. So that's fine. But on the interval from -1 to 1, this expression is negative. So when you take the absolute value of it, you'd multiply the result, that negative number, by -1 to get the absolute value of it. So on this interval, you'd end up with a 1 minus x. That's the same as this times -1 over x plus 1. For x in between -1 and 1. Okay, so we don't actually know the interval. We weren't told what the interval of existence was, and we were not given an initial condition which would allow us to choose an appropriate interval of existence. So since we don't have more information, what I would recommend is, well, let's look at the differential equation itself. We have to be on an interval where 1 minus x squared, the square root of 1 minus x squared, is well defined. So I guess we need to look at that one as well. The square root of 1 minus x squared is the square root of 1 plus x times 1 minus x. And the interesting points there are at x equals -1 and x equals +1. 1 plus x is positive over here and positive over here and negative here. 1 minus x, well, if x is, say, -2, it's going to be 1 minus a -2, that's going to be +3. If x is 0, we'd have a positive. If x was 2, 1 minus 2 would be negative. So this is going to be negative there, and the product will be negative there, the product will be negative there, and it will be positive there. Okay, so this is actually only well defined on the interval from -1 to 1. I'm glad we went back and checked that, because that tells us that this absolute value this absolute value raised to the 1/2, it's this on this interval and this on this interval, but our differential equation is only well defined on the interval from -1 to 1, which actually makes sense. If you look at the graph of y equals 1 minus x squared, that's positive on the interval from -1 to 1. And it's 0 at the end points, but this function over here is not defined at -1, and it's equal to 0, which means the logarithm's not defined there. So yeah, we're not interested in those endpoints. So this is actually the interval we're interested in. Now that was a lot of work just to get that. But if that's the interval we're interested in, then this is the integrating factor, or this is the factor in the integrating factor that we're interested in. So the integrating factor is e to the x times this, and this expression is actually this one. So I have e to the x times this guy, and because we are looking for an interval where that original square root of 1 minus x squared is well defined, this turns out to be the square root of 1 minus x over x plus 1 times e to the x. And we're on the interval from -1 to 1. So we can keep that in mind. On the interval from -1 to 1, 1 minus x is positive, and x plus 1 is also positive. Okay, so now we've got our integrating factor, finally. So we're going to take our differential equation in standard form, and we're going to multiply it by our integrating factor. And the differential equation looked like this. We had dy dx minus x squared over 1 minus x squared times y equals this over here, 1 plus x over 1 minus x squared to the 1/2. And make sure that that's right. Yeah, 1 plus x. Okay. So take this differential equation and multiply by that integrating factor. Okay. Now, we should try to simplify if we can. And we can a little bit. This is 1 minus x over 1 plus x times e to the x. Over here, if we factor out that y, we've got a negative x squared here. Then we've got a 1 minus x to the 1/2 power over this, which is 1 minus x times 1 plus x. And this is a 1 plus x to the 1/2 power. And we can do that again because we're on the interval from -1 to 1. And on the interval from -1 to 1, both of these factors are positive. So splitting this up works because both of these factors are positive on that interval. And then over here, we should simplify as well. We've got a 1 plus x and a 1 minus x to the 1/2. This is a 1 plus x to the 1/2 times 1 minus x to the 1/2, because that is a 1 minus x times 1 plus x, all raised to the 1/2, so you can distribute that. Because if you have a times b raised to a power, you can apply the power to each of those factors. And then don't forget this 1 plus x to the 1/2 that's in the denominator there. Okay, great. With that in mind, let's see. We've got a 1 plus x here. We've got a 1 plus x to the 1/2 and a 1 plus x to the 1/2. So those reduce. because that's a 1 plus x divided by 1 plus x, which is 1. And is that really true? Yeah. I guess we get these guys cancel as well. And don't forget your e to the x over here. Very nice. That worked out really nicely. Normally it doesn't work out that nicely. Let's see, is there anything else that simplifies like that? Well, this guy simplifies a little bit. You've got a 1 minus x to the 1/2 here and a 1 minus x to the first down here. So that's going to reduce, if there's a 1 there, the 1/2 minus 1 is a negative 1/2. So you've got the square root of 1 minus x over 1 plus x times e to the x times dy dx minus x squared, and then the 1/2 minus 1 is a negative 1/2, which leaves us with a 1 minus x to the positive 1/2 in that denominator. Now I've got a 1 plus x and a 1 plus x here with different exponents, so we can add those exponents. It's going to give us a 3/2. Okay. Now, provided we've done everything correctly, this should be the derivative of this with respect to x. Remember how this works. Bernoulli's brilliance was this. He said, if we multiply by just the right thing, then this left-hand side is going to be the derivative of y times the integrating factor. So this should be, if we've done everything correctly, the derivative with respect to x of y times the integrating factor, which is this square root times e to the x, or 1 minus x over 1 plus x to the 1/2 times e to the x. And because everything worked out so nicely over here with all of these cancellations, we just have an e to the x on the right-hand side. So that is our next step. We're just recognizing that the left-hand side is the derivative with respect to x of y times our integrating factor. Now, you should check that out and make sure it actually works. And it turns out that it does work this time, but just to check, think of this as this up here as a result of a product rule. If this is your first function and this is your second function, derivative of a product is the derivative of the first times the second plus derivative of the second times the first. So the question is, well, that's obviously the derivative of the first times the second. And this is obviously the first. Question is this a derivative of the second function? Is this equal to the derivative of this? Now, if it was a quiz, I wouldn't check. I would just go on and assume that the left-hand side is what it's supposed to be. But if it's an easy check, it's always a good idea to check just to make sure that you're on the right track, that you haven't made some kind of sign error. So let's check. If I'm taking the derivative with respect to x of this product, 1 minus x over 1 plus x to the 1/2 times e to the x. This is a function times a function. We get, by the product rule, derivative of the first. Derivative of a function to the 1/2 is 1/2 times that function to the negative 1/2. Put the inside function back inside, and then multiply by the derivative of the inside by the chain rule. So that's derivative of the first times the second, plus derivative of the second, in this case that's e to the x, times the first. Okay, now we just have to finish this. Couple more things. If I've got a quotient raised to a negative power, you can just flip that fraction and raise it to a positive power. There's a reason for that. If you're not sure of the reason, come see me and we'll talk about it. So this 1/2 of this raised to the negative power is the same as a positive 1/2 times that, but take the reciprocal and then raise it to a positive 1/2 power. And then we have to take the derivative of this quotient using the quotient rule. Okay, now the quotient rule says if this is the top function or the high function and this is the bottom function or the low function, we get low d high, which is the bottom function, times the derivative of the top function. In this case, the derivative of the top function is -1, minus high, that's minus the quantity, 1 minus x. Don't forget those parentheses, otherwise you're going to have the wrong sign there. Times the derivative of the low function, that's +1. All over the bottom function squared. And that's multiplied by e to the x, and that's added to this 1 minus x over 1 plus x, all raised to the 1/2 times e to the x as well. Now we want to simplify here where we can. And remember, 1 plus x and 1 minus x are both positive on the interval that we're interested in. So we can write that as 1 plus x to the 1/2 over 1 minus x to the 1/2, just applying that exponent to the numerator and denominator. Over here, if we distribute the -1, we get -1 minus x. Distribute the -1 here as well. We have a -1 and a negative times a negative x is a positive x over 1 plus x quantity squared. And we still have a 1 minus x to the 1/2 here and a 1 plus x to the 1/2 here and an e to the x. Well, the x and the negative x reduce. And now you've got a -2 and a +2. So it's going to reduce to a -1. -2 divided by +2 is -1. So we'll have -1 times 1 plus x to the 1/2 over 1 minus x to the 1/2 times 1 plus x to the 2nd power. And I'm going to factor out that e to the x. Now I notice right away that this doesn't look like the expression that I'm going for. I'm trying to make this look like this. That denominator has a 1 minus x to the 1/2 and a 1 plus x to the 3/2. So I'm trying to make that denominator look like that. And I do see that this 1 plus x to some power over this 1 plus x to some power, that can simplify. We can subtract the exponents. So 1/2 minus 2 is -3/2, which would mean we'd have a 1 plus x to the +3/2 in the denominator. And that's good because now that looks like this. Now in order to add these two fractions together, I'm going to need a common denominator. So I'll say, what do I need over here? Well, I've got a 1 plus x to the 3/2, and here I have a 1 plus x to the 1/2. So I'm going to need another 1 plus x to the first, because 1 plus x to the first times 1 plus x to the 1/2 is 1 plus x to the 3/2. And I also need a 1 minus x squared, or 1 minus x to the 1/2, excuse me. Okay, let's see what we get when we do that. So now we've got a -1 over here over 1 minus x to the 1/2 times 1 plus x to the 3/2. Here you've got a 1 minus x times a 1 minus x, which is just going to give you a 1 minus x times a 1 plus x over a 1 minus x to the 1/2. And this is going to be a 1 plus x to the 3/2. And now that we have a common denominator, we can just add the numerators. So you have -1 plus, if you distribute there, first times first is 1, outer times outer is x, inner times inner is -x, x minus x is 0, and then last times last is -x squared. And these guys reduce. And it is exactly what it was supposed to be, -x squared over 1 minus x to the 1/2 times 1 plus x to the 3/2 e to the x. I know that that was a lot, but it was good that we did it, because now we know that this left-hand side truly is the derivative of this product. Now, if we had chosen one of these, if we had chosen this to be our simplification of that, we would have been wrong. The derivative of this, where this absolute value expression is replaced by this, doesn't give us this right here. That came from the fact, that extra negative sign actually came from the fact that we chose this one, which has that negative x in the numerator. And we know that we were supposed to choose this one because this was part of our original differential equation. Remember, we had that square root of 1 minus x squared on the right-hand side. So that means we have to choose an interval where that product is positive, and that product is only positive on this interval from -1 to 1. Since this is well defined here, we have to choose this to be equal to this because we're interested in that interval only. Okay, so now we are 2 steps away from getting y by itself. We have the derivative of y times the integrating factor equals e to the x. We want to get rid of the derivative, so to get rid of the derivative, we'll anti-differentiate. We get that. Derivative and antiderivative undo each other, and we just end up with y times the integrating factor. Equals the antiderivative of e to the x, which is our favorite antiderivative. It's the easiest, e to the x plus c. And we're trying to get y by itself. So you can divide both sides by e to the x. Now I feel like I'm going to a theme park. I'm from Florida, you know. So we're going to divide both sides by e to the x now. And we have this. I don't know if you guys have ever been to Universal Studios or Busch Gardens, standing in line, at least in the 90s. I don't know, it's been a long time since I've been to Busch Gardens. But they'd say things like, get ready to feel the sting of the scorpion. We're just gonna divide both sides by e to the x, and then we're gonna multiply by the reciprocal of this to get y by itself. That's what that reminds me of. Excuse my little asides. Not the best comic relief, but I do what I can. We're multiplying by the reciprocal of that on both sides to isolate y. And let's see, that reduces with that, and that reduces with that. And we have y of x equals this expression, which you could write a number of different ways. You could take each of these guys and divide by e to the x. So you'd have 1 plus c times e to the negative x times this quotient, if you prefer. Or you could have this times an e to the negative x times all of that. There are lots of different ways to do it, but I think I'll stick with this one. And we know, because of all of our analysis, that the maximal interval of existence is -1 to 1. So that's how we do that. So remember, we did a lot this time. Let's talk about solving first-order linear differential equations. It's actually just a few steps, but those steps are pretty involved, and there was a lot of algebra on this one. First, we write the differential equation in standard form. Then we identify P and anti-differentiate it. You could start by adding a well-chosen 0 and separating the numerator. You can also use long division to get here. And then when you get here, you say, I'm gonna have to use partial fraction decomposition for this. So use partial fractions for this, which gets you here. And then you anti-differentiate. And you choose c to be 0 because you only need one integrating factor, not infinitely many integrating factors. Then e to that power is your integrating factor, which gets us here. And then we had to be really careful about domain issues. We said, okay, I cannot take the log of 0. So x is not allowed to be 1. And this absolute value is, of course, always positive, but the version of that expression, x minus 1 over x plus 1, that I should use depends on which interval we're on. this quotient is positive on the interval from negative infinity to -1 and positive on the interval from 1 to infinity, but it's negative in that interval from -1 to 1. So we said, that means that this will be positive on these two intervals. So we can just take the square root of that positive number. And I said, but at this middle interval, this number is actually negative when we evaluate it for x values in that interval. So we'll multiply that negative number by a -1, which gives us that 1 minus x instead of the x minus 1. And that is now positive because we multiplied it by -1. Negative times a negative makes it a positive. Then we take the square root. And that works on this interval. And then at first I was thinking, okay, we've got two options. We're either here or here, and the initial conditions will tell us which one we should use. But then I said, aha, remember, the right-hand side of that differential equation has this in it. And that is only well-defined on this interval. The product is only positive between -1 and 1. Or you could just look at the function y equals 1 minus x squared, and we can see that that's positive on the interval from -1 to 1. So this is well-defined on the closed interval from -1 to 1. This is well-defined on the open interval from -1 to 1. X can't be 1 because we can't take the log of 0. X can't be -1 because we can't divide by 0. So this is the interval of existence for our problem at this point. So we're going to use this for this factor, and that's our integrating factor. Okay, back to the big picture. You write the DE in standard form, you identify P, and you antidifferentiate. You define the integrating factor, and then you multiply the differential equation by the integrating factor. And that's the differential equation in standard form. And then once you do that, you say, hey, that means the left-hand side is the derivative with respect to x of y times the integrating factor. If you have a quiz, you don't have time to check that, you can just say that that's true, then you're 2 steps away from getting y by itself. In order to get rid of the derivative, we anti-differentiate both sides with respect to x. And then you've got y times the integrating factor equals this, and if you're trying to get y by itself, you have to divide by that integrating factor. So that required dividing by e to the x and then multiplying by the reciprocal of that fraction. You could have divided by the whole thing in one fell swoop if you wanted to, but I find it easier to think through it this way. So you're just dividing by the integrating factor to isolate y. And then you state your general solution and the interval of existence. And this will be well defined all the time because e to the x is never 0. And this we're going to have problems whenever x is equal to 1 or -1 because of the issues that we talked about earlier as we were proceeding through the method. So our maximal interval of existence is right there. I guess we could plug in x equals -1 to this, but x equals -1 does not satisfy that. So we would have to check the possible answer x equals -1 up here and see if it satisfies the differential equation. And I don't know that it would. Anyway, that's how we solve that differential equation. I know that was a long one. Thank you for your patience and your time.